All right. So the next few weeks on Mondays, I'm going to be breaking up the kind of teaching of Module 12. It goes along with the curved arrow mechanisms that we've shown so far. What I'm going to do the rest of the year is introduce specific kinds of reactions using the curved arrows. And the first one I'm going to focus on what we call acid-base reactions. Can I not move this? Oh well. So I want to start by just defining. Today is going to be a lot of definitions. I apologize for that. And then we'll get into more like chemistry explanations later. But I want to start by defining acid-base reactions. So acid-base reactions are reactions where an H plus ion gets passed from one molecule to another. So anytime we have a reaction where all that's happening is H plus is going from one molecule to another molecule, we call that an acid-base reaction. We also have another name for it. If you think about it, hydrogen, it's the first element in the periodic table. So how many protons are there in an atom of hydrogen? One proton. And how many electrons? One. So if you take away the electron and make it H plus, what's left? Just the proton. So we also call these proton exchange reactions. Essentially, the terms H plus and proton are synonymous. So these reactions are also known as proton exchanges. And what I put down here is pretty much a classic example. HCl, you may remember that molecule. Everyone has pretty much used this in their first year of chemistry. What do we call that chemical? That's hydrochloric acid. And when you put hydrochloric acid in water, it generally gives the H plus to water in a reaction that looks like this. How would I draw the curved arrows to complete that reaction? Think back to our rules for how we draw curved arrows. When we draw curved arrows, we draw arrows from where to where? From negative to positive. So if I'm going to form a bond from oxygen to hydrogen, who's partially negative and who's partially positive? Oxygen's partially negative, hydrogen's partially positive. So I would draw curved arrow from a lone pair on oxygen to hydrogen. That will form this new bond. I'll highlight in pink. And then hydrogen can't have two bonds at the same time, so I need to break the bond between H and Cl. Who gets those electrons? Chlorine. So that gives chlorine the extra lone pair that gives it a negative formal charge. For acid-base reactions, this is what the curved arrows always look like. Generally, it's a lone pair from one atom going out, forming a bond to the hydrogen, and then you break the bond from the hydrogen and give the electrons to the other atom. Terminology, the thing that is giving up the proton is called the acid. So in this case, HCl would be called the acid because it's the proton donor. We would say it's donating its proton to water. And then water, the proton acceptor, is called the base. And we have words for the products in this reaction too. After HCl gives up H plus, becomes Cl minus, notice that Cl minus could go out and grab that H plus back. So Cl minus could act as a base. And the word we give it when it's the product of the reaction like this, we call it the conjugate base. And then H3O plus in this case would be called the conjugate acid. So in general, every acid-base reaction is like this. You have an acid that gives up a proton, a base that accepts a proton, and then you form the conjugate base that now has lost the proton, and the conjugate acid, which is the thing that has gotten the proton. Questions about those terms? All right, on we go. Just in general, this won't always be HCl and water. So in general, we often draw this as HA and B. So HA is like standing in for our generic acid. So if you ever see HA and you're confused because you're like, hey, A isn't on the periodic table anywhere. What is HA? The A there is standing in for whatever the rest of the molecule is. And then a lot of times you'll see B acting as a base. That's not representing boron. It's just representing some base that we don't want to specify. So that's our generic base. And the curved arrows always have an arrow from the base to the hydrogen, and then breaking the HA bond to make your conjugate base and conjugate acid. So I say that, this is a general form because this reaction can happen in lots and lots of different situations. Essentially, any molecule that has a hydrogen in it could, in theory, act as an acid. But most of them don't act as an acid, at least under normal circumstances. So a lot of what we need to parse out is figuring out, okay, what kind of things will act as acids, what kinds of things will act as bases, and when will these reactions happen? It turns out these acid-base reactions are pretty much the most common kind of reaction, and they're always happening billions of times per second in any solution. So if you have a bottle of water, this is going on just between water molecules, where one water molecule gives up H plus to another water molecule. They make H3O plus and OH minus. It's happening all the time. And a lot of what our job is in organic chemistry is figuring out what kinds of things will act as acids under what circumstances, what kinds of things will act as bases under different circumstances. So we introduced this idea that we call acid strength, because what we want to do is put acids on a scale from, what are really, really good acids and all the way down to what are really, really bad acids. And we call that acid strength. So acid strength is a measure of how strong an acid is. What that means is how willing is it to give up H plus. So the strength of an acid is how willing it is to give up H plus. So what that means is something that doesn't hold on to H plus very tightly is what we call a strong acid. Something that holds on to H plus really tightly, we would say is a very weak acid. So a stronger acid gives away H plus more readily. In reality, usually what happens in a solution is only a percentage of the molecules will actually give up their H plus. And so for a stronger acid, that percentage is much higher. For a weaker acid, the percentage that gives up H plus is much lower. And the word we use for that is dissociate. All right. Uh, so when we say the acid gives up H plus, we say it dissociates because the H plus and the A minus are separating. So that word is dissociation. So for a stronger acid, a greater percentage of the molecules will dissociate. For a weaker acid, a smaller percentage dissociates. And those percentages can run from, 0.000000001% all the way up to like 99.999999%. So it's a broad range that we deal with in organic chemistry. So when we want to talk about acid strength, we need to have some sort of scale to measure them on. And we won't go into the math in this class. Organic chemistry doesn't usually involve a whole lot of math. In AP chemistry or general chemistry, we do go into the math of the calculations, but not in here. Um, in here, essentially, what we're going to say is we have a number that we use to describe acid strength, um, and the number that we will tend to use is called pKa. And what you can think of pKa as how hard it is to pull H plus away from the molecule. So what that means is if something has a high pKa, will it give away H plus easily? High pKa won't give away H plus easily, which makes it a weak acid. So a higher pKa means a weaker acid. and a lower pKa, that means it holds H plus weakly. And if it holds H plus weakly, that means it's very willing to give away H plus, which makes it a stronger acid. Now, in a typical college orgo class, you would probably have to memorize a bunch of pKas. I know in the class I teach in the summer, I don't know, students end up having to memorize about 15 pKas over the course of the year. What I'm going to do is give everyone a reference sheet. So I'm going to hand those out now. Okay, take a look. Take a look at the reference sheet. So the front side of the reference gives you lots of organic functional groups where the pKas start at 50, which is a really high pKa. Those are H's that you can almost never remove. Going down to about -2. -2, really easy to remove. And then on the back, I actually gave a bunch of acids that are considered strong acids. So those all have pKas of 0 or lower. So those are all H's that are really easy to remove. So on the back, you see things like hydrochloric acid, which we said you've all used before because it's a really common strong acid. So the scale, there's no like absolute boundaries to the scale, but the scale is pretty wide. We have examples going from -10 up to 50, right? But one of the things we want to be able to do is use this list to compare molecules and be able to say which molecules are most likely to give up H plus, which molecules are most likely to take H plus from others. And I think that's good enough for one day. Next time we'll start talking about what makes one acid stronger than another. And we'll talk about how the strength of bases relates to the strength of acids, etc. Questions before we quit? All right.